let's see. So first, just sort of summarize, we're going to be all Chapter 5. And so when you're looking at Chapter 5, that's on our work and energy chapter, those will all be from Exam 3. And usually that's the first dozen or so questions for Exam 3. But if you get to momentum, if you find anything that says anything about momentum, then you know you've gone too far. So just stop, and that's the last question. If you have questions about that over the next few days, you can just email me, and I'll tell you. It's like, oh yeah, that's the end of Chapter 5. I think you'll be able to tell once you see it. That's going to include work, and I break that down into two different categories. So you'll see problems that are calculations problems, and then you'll also see conceptual questions about that. So the work that a force will do, you'll probably just have one where you have a force that, where you have a force that's at an angle and you have to figure out what is the work done. Then you'll also have some spring questions where you have to calculate the work or the energy due to a spring. And then maybe also for Hooke's law, F equals minus kx, you'll see energy. And both of those I'll have both calculation and conceptual questions. So you'll probably have a problem where we do like the roller coaster like we did in class the other day. We'll do one of those here. You will have one like that. You'll probably have some questions that ask you about the relationship between KE and M, KE and V, or V squared, or about the potential energy and its relationship to H. Potential energy is mgh. You will have an equation sheet. So if you go on the website, I'm going to give you just the Chapter 5 equations. So you'll have all of this right here for the quiz. Okay? You might have a power problem as well. Okay, so let's look at some of these. Like I said, hey Courtney, you'll have a question. Amy? Welcome. Good to see y'all. All right. You have a conservation of energy question, just like we did, what was that, yesterday we did these? Where I'm asking you about the speed or the height of an object at a particular point. And in these, you're always going to say that the energy at one point, that it would be the kinetic energy plus the potential energy, will equal to the kinetic energy plus the potential energy at another point. So here, I'm looking for the speed at point B. So that'll be my final position. And I'll take A to be my initial position. I'm taking A because I know what the speed is at point A, and I know what the height is at point A. So I know everything there is to know about point A. I also know that at point B, one of the energies is equal to 0, and you'll need to identify which energy that is. Which one is it that's equal to 0? At point B, which energy? The kinetic or the potential energy at point B is equal to 0? Potential, right. So the potential goes away, and then I'm left with 1/2 m. I'll go and put in the numbers, just saves a little time. 10 meters per second squared. That was the speed at point A, plus m times g, that's 10, times h, which was 30. That's the height at point A, is equal to 1/2 m times v squared, which is what we're trying to solve. Then I can cancel out the m's. As long as I don't have a spring, if I have a spring, the mass won't cancel out. But as long as I don't have a spring, then the mass will always be irrelevant. Doesn't matter. So I have 50 plus 300, that's 350. So v squared looks like it's 700. So v is the square root of 700. Must be 26. Is A the right answer? I think I did that right. Yeah, 26 is the right answer there. You'll definitely have a problem like that, okay? You might also have a problem like number 3, and students sometimes have trouble with this. Yeah, like number 3, where I have a block that's sliding along a rough surface, and it loses its energy as it's sliding along. We're going to do these tomorrow in class, but let's go ahead and take a look at it now. So I have this block that has a speed, an initial speed equal to 4 meters per second. And then it has a final speed equal to 2 meters per second. So it begins with a certain amount of energy, and it ends with a lesser amount of energy, right? Because it slows down, so it has less kinetic energy. That change in energy, by the way, the amount of energy that it's losing is going to be 1/2 of its mass, that's 10 kilograms, 1/2 m times vf squared, that's 2 meters per second squared, minus 1/2 of my mass, which is 10, times 4 meters per second squared. So that's going to be 5 times 4, that's 20, minus 5 times 16, what's that, 80. So I lose 60 joules of energy. That's what the negative means, that I'm losing 60 joules of energy. Now that energy is lost because the frictional force acts on this block. So the work is equal to my change in energy. The work is equal to the frictional force times the distance that it travels, and that's equal to my change in energy. So my frictional force is going to be, well, I need to find out what that's going to be, times the distance, it traveled 2 meters, is equal to minus 60 joules. Now I know this is going to be -2 because I know that the force and the displacement are opposing directions. So that tells me that Fk is equal to 30 newtons. Okay, so the final step here, I'm looking for the coefficient. I'm going to say that Fk is equal to mu times the force normal. So that's going to be 30 equals mu. The normal force is 100. I got that because it's 10 kilograms. 10 times g is my normal force. This is on a flat surface, so the normal force equals the weight. And so I get the coefficient is equal to 0.3. You'll find a question like that on almost every exam, where I have some object that's sliding across a rough surface, it loses energy, and you have to tell me something about the frictional force. That's probably one of the most difficult questions on the exam. Okay? Y'all could do that if I gave it to you tomorrow? Or right now? Let's take the quiz right now. You want to take it right now? No. Okay. Hey, how's it going? Yeah, right. Okay. You'll have some conceptual questions like number 2. Let's go on and look at some others, though. Okay. Let's look at number 5 and at number 8. So these are all types of questions that you'll have. If you look back at the past 5 years of exams, frankly, you'll see that a lot of the questions are very similar. So, you know, I'm asking about the same kind of stuff. They're just framed in different kinds of ways. But as you practice those questions, you'll get the hang of it. Let's look at number 8 first. I'm looking for the total work. We did this in lab this week where we had the inclined plane, and I asked you what was the net work, or that is, what is the total work that's done, where you had a couple of forces and you had to add up those two amounts of work that were being done. This is asking that too. I have this force of 8 newtons that's applied at 60 degrees, and it makes it move over a distance of 3 meters. So the work done by this force is going to be Fd cosine theta. That's going to be equal to 8 times 3 times cosine of 60. So that's equal to 12 joules. And it is positive because the cosine of 60 is a positive value. And then the other work that's being done is the work being done by this force. And that work would be F times d times cosine of theta. That would be 1 newton times 3 meters times the cosine of 180. The 180 comes about because the frictional force is to the left and the displacement is to the right, and so those two vectors are separated by 180 degrees. If you just want to think, oh, I know that work is negative, that's fine too. You could just leave off the angle because cosine of 180 is equal to -1. So I would get -3 joules there. So the total amount of work would be 12 minus 3, which is 9 joules. Okay? Oh, because I'm asking for the total work that's being done. I'm not asking for the work done by F. I'm asking for what is all of the work that's being done on this object. Okay? Let's look at number 5 too, because you are going to have a spring question, probably a conservation of energy, and that's what this is. This is a spring, as a spring constant. That's my K value right here. It has a 4 kilogram block. That's the mass. I compress a spring a distance of 2 meters. That's X. That refers to the X that you compress the spring, the 1/2 kx squared. And you allow it to oscillate. I want to know the speed of the block when it passes through the equilibrium position. At the equilibrium position, that is x equals 0, I can have elastic potential energy, or I can have kinetic energy, or I can have both. Which one do I have? Does it have elastic potential energy? Does it have kinetic energy, or does it have both? Which ones does it have? When it goes through the equilibrium position. And remember, at the equilibrium position, x is equal to 0. So what does that tell you about those two values? Well, I know Ke is 1/2 mv squared. And I know that the elastic potential energy, that's that PES, is 1/2 kx squared. So what type of energy do we have at the equilibrium position? We only have kinetic, right? Because x is equal to 0, that goes away. So at the equilibrium position, that's the type of energy that I have. And then if the spring is compressed all the way, where here it says that it's compressed to x equal 2 meters, over at this point, the speed of the block is equal to 0. So I compress that spring, the block isn't moving, so it only has what type of energy? It only has elastic potential energy. So over here, I have elastic plus kinetic energy, but the kinetic energy is equal to 0. So I'm going to set that elastic potential energy, 1/2 kx squared, equal to the kinetic energy at the equilibrium position. That would be 1/2 mv squared. My halves will cancel. I have K was 1200, X was 2 meters, equals the mass is 4 kilograms times the speed, which is what I want to find, is squared. That's 2400 divided by 4, 600, square root of 600. Must be 35. Is that 35? Did I do that right? Let me make sure. 600 divided by 4. 24 divided by 4. Oh, there you go. I didn't square the x. Yeah, and that cancels the 4. So it's actually the square root of 1200, and that is 35. I'm pretty sure. Okay? Probably going to have a question like that. That would be, I would consider that a conservation of energy problem, but considering springs. Make sure you know how to find your units for work. You just start with the equation. We're going to see these more as we move along. Work is equal to F times D. I know that F actually is mass times acceleration. That's Newton's second law. So kilograms, meters per second squared, meters. So the total units for work is going to be a kilogram meter squared per second squared. These are other force problems, like number 6 would just be using F equals minus kx, that's Hooke's law, to find what is the spring constant. So here I had 12 is equal to something times 3, so that's going to be equal to 4. All right. Let me make sure I get all your names here. And it's Maya. I'm sorry, what's your name? Maya. Scott. All right. Y'all have any particular questions looking at these? So for example here, we would stop at number 12. I see a collision, no collisions on this quiz at all. That'll be next quiz or next exam. Particular questions? I don't think it's going to be a particularly difficult quiz, like if you're prepared. I mean, if you're prepared, nothing's difficult, right? Is that true? Well, that's not true. But if you're prepared, you'll do well. But just make sure that you're prepared. Let's see, what type of energy does this object have at point A? Well, it has a height at point A. It says it also has a speed. So what type of energy does it have at point A? It has both, right. It has both potential and kinetic energy. Number 3 is another conservation of energy. I want to find the speed of the ball or the bead at point C. So I would have 1/2 mva squared plus mg, the height at point A, is equal to 1/2 mvc squared plus mg, the height at point C. So VA would be 4 meters per second. HA would be 5 meters. VC is what we're looking for. And then HC would be 2 meters. Notice your masses all cancel. And then you would solve for VC. Let's look at number 4. So this was that, remember I said this is probably the hardest problem on the exam. So let's think about this, how we would go about this. This is a really similar one to the one we did on the previous exam. I have this cardboard box. It has a speed of 2 meters per second. And it slides along the floor. It says that the mu is equal to 0.2. The mass of this box is 3 kilograms. By the way, that will tell me that the weight of the box, which is equal to the normal force, is going to be equal to 30 newtons. And I want to know how far does it slide before it comes to rest. Initially, this box only has kinetic energy. It has kinetic energy that's equal to 1/2 mv squared. And then the frictional force is going to do work that will take away all of that energy. So I would say that 1/2 mv squared minus the frictional force times the distance will equal to 0. All that kinetic energy that the box has, as it slides across the floor, that frictional force will take away that energy. So I know a lot of this. I have 1/2 m is 3. Its initial speed is 2 meters per second squared minus, I don't know the frictional force, but look, I can find it. The frictional force is mu times the normal force, so that's 0.2 times 30 newtons, so that's what, 6 newtons? So 6 newtons times the distance that it travels. That's what I want to know. I want to know how far does it travel, and so that's going to be equal to 0. So I have a 6 minus 6 times d equals 0. So d is going to equal to 1 meter. Okay?
So when the kinetic energy and the work equal the same, that's when the box stops?
Yeah, because that work that's being done by friction has to take away all of the energy in order for the box to stop. And it says it does stop. In the previous one we did, I'm sorry, you came in, I don't think you saw that, but on the previous exam, it didn't stop. So we had to take into account the change in kinetic energy. Let's go back up just to remind y'all about that. We had to take into account the change in kinetic energy right here, instead of where it had a change in 60 joules, a change of energy of 60 joules. Okay? Is this easier than the previous chapter, than chapter 4?
Like it just hasn't clicked yet for me.
Hasn't clicked yet. Okay, that's probably true for a lot of y'all. So it's wrong for me to say that it's easy, but once it clicks, I think that you will find that it is less complicated. It's not dealing with all those vectors. Those vectors, fuzz up people's minds or whatever. All right, let's keep looking here. Let's go down a few exams. I'm only taking from the last 5 years of exams, so keep that in mind. So there are only about 50 questions that I'll pull from. Not that many questions really, and a lot of them are similar. So I would print out the last 5 years there on the Moodle site and try practicing those. When you can get them all down, even if I do them 3 or 4 times, then you'll be ready for the quiz. Use the videos at first, but then try to move away from those. Well, let's look at some of these. So this 2 trailers, we don't talk about ratios that much, but it's useful for standardized tests. Standardized tests do like to offer ratios. That's why I put this on here. I wanted to know, I have these 2 trailers. They have different masses and they're being pulled at the same speed. I want to know the ratio of the kinetic energy of y to x. So I want to know what is the kinetic energy of y to kinetic energy of x. Was somebody singing? Were you singing?
Oh, I was talking to myself.
Oh.
I was writing down
All right, the kinetic energy of y to x, that's the ratio. Well, is y bigger or smaller than x, the kinetic energy?
Bigger.
Bigger, right, because it has a bigger mass. And I know that kinetic energy is proportional to the mass. It's a direct linear relationship. So I see that this has a mass of 2,000. This has a mass of 500. So I could say that the ratio, I could just put in this 2,000 to 500, which reduces down to a 4-to-1 relationship. All right. If the colon confuses you, just write it as a fraction. 2,000 over 500, it's the same thing, a 4 over 1. Now, if it were speeds, say, for example, trailer X had a speed of, 2 meters per second, and trailer Y had a speed of 4 meters per second, then the ratio of KE to KX would it be 2 to 1? Right. Yeah, it's a quadratic relationship. So it's going to be a 4-to-1 relationship. Yeah, 4-to-1. Because the kinetic energy is proportional to V squared.
Do you square them and then relate them?
Well,
16 to 4 is 4 to 1.
yeah, 16 to 4 is 4-to-1. Yeah, so yeah, you would say 16 to 4. That would be 4 squared to 2 squared would be 4-to-1. Okay. Let's look at number 13. Number 13 is like one that we did before. Similar, but it's a little bit different just because it's on an inclined plane. I have this block on an inclined plane. I pull it across a distance of 2 meters. What is the total work being done on the block? So it's actually, don't let the inclined plane throw you, because it doesn't really matter that it's on an inclined plane, because I give you this force and I give you this force. So the total work is just going to be force times distance, that's 20 times 2, minus force times distance, that's 5 times 2. And I say minus just because that little f is opposing the direction of the displacement. So that's 40 minus 10, or 30 joules.
And what's the equation for work again?
Yeah, so work is equal to F times D times cosine of theta. In this case, theta was equal to 0, and over here, theta was equal to 180. That's where the negative comes from, because cosine of 180 is equal to -1.
It's because they're parallel, right?
Yeah, FD is in this direction, and so this big F is parallel with D. The little f is what we call anti-parallel, or it's in the opposite direction. Okay? So you'll see some questions like that.
But so like when they're running the exact same, like even though it's technically going in a different direction, you don't have to worry about the angle, right?
Right, yeah. So I didn't need to worry about the angle of the incline at all. Yeah, because the distance, I knew the direction of the displacement, and I knew the direction of F, the two forces. Now, if my energy changes by 30 joules, this is just like lab we had this week, I want to know what is the change in height of the object. This is where the angle does become important. So my energy, actually no, I don't need to know the angle at all, I'm sorry. So my energy changes by 30 joules, and all of that energy goes into potential energy for the block. So that 30 joules, I would say, is equal to the change in potential energy. So 30 equals m times g times h. M is given, that's 30 equals 3 times 10 times h. So h is equal to 1 meter. So I found the change in height just by setting that change in energy equal to the potential energy of that object. It's a really powerful way to look at things, because this problem, which we did in chapter 4, becomes a lot easier here. Really a lot easier. Yeah, yeah. So we'll do a different one. This one is simple, but we haven't done one like this yet. So let's go ahead and look at this. Number 11 is just asking, what is the force? So I have a displacement that's in that direction that's equal to negative 50 centimeters. I say it's negative because it's to the left. And so I want to know, what is the force? The force is going to be that force that the spring exerts on the block. That force will be equal to negative k times the distance. Let's see, I call that x. I'll call this x up here. That's going to be negative of k, which is 1,000, times negative 0.5 meters, converting that into SI units. So that's going to be 500 newtons. If you get all wrapped up in the signs, just look at the picture and think about the picture. I mean, here the signs came out right in the end because I was careful about making sure that I have x equal to negative 0.5 meters. But I do know that this spring right here is going to exert a force in this direction, because if this is my equilibrium position and I push that spring to the left, then the spring is going to push back to the right. So hopefully you can see that that force should be to the right. That would be positive. But notice that if you weren't sure, that you might have gotten C, but you also might have gotten A. So just look at the picture. If I give you a problem like that where it's important, then I will give you a picture just so you can imagine it. Right, the other alternative would be that if this is the equilibrium position, that I pull the spring back in this way. And in this case, the force is going to be in which direction? To the right or left? So I pulled it away from the equilibrium position. I pull that spring to the right, past the equilibrium position, and then the force is going to be in which direction? To the left, right? Because the force is always towards the equilibrium position. The block wants to go back to that equilibrium position. So the force, it doesn't want anything, but it tends to go back to that equilibrium position because that force will always be towards the equilibrium position. Okay? Let's see what else we got. We haven't done graphs. I don't know that we'll do it, but because it's on the exam, it could be on your quiz. Work is equal to force times distance. So if I have a graph of force times distance, then the total amount of work would just be the area under that graph. So here I'm always pushing it across a distance of 4 meters. So that would actually be the area of this section. So that's 0 to 30. So 30 on the y-axis, 0 to 4. 30 times 4 is 120. I think that's the only graphing problem that I've had ever in the last 5 years. I think there were some older ones back, but just remember that work is force times distance. So if I have a graph of force and distance, then I take the area under that graph. But again, your questions are going to be exactly like these, not changing numbers, not changing figures, exactly like this. So just be prepared if you see that. All right, you'll have some conceptual questions. Let's look at this one. Which of these statements is true? It's moving up the inclined plane with a tension force and a frictional force. Okay, is the frictional force bigger than F? Now that can't be true, because if that were true, it would actually be moving down the inclined plane. The frictional force increases as the block accelerates. No, that's not true. That we'll have a constant. Does the force F do positive work? Well, the question there is F and the displacement in the same direction? If they are in the same direction, it does positive work. If they aren't, it does negative work. Same direction?
Yes.
Yeah, so that must be the right answer. And then the frictional force is in the negative x direction with a typically chosen coordinate system, where a typical coordinate system looks like this. And so F is actually in the positive x direction. That's sort of throwing back a little bit in the last chapter. All right? Here, it ended at 19. Oh, that was a lot of questions on work and energy in that exam. All right, I'll just sort of scroll through some of these. Y'all holler out if you see something. Can we do number 1? Is that okay? This is another one of those. This is the hardest question on the exam, okay? So you'll probably have one of these on your free response, by the way. And we'll wrap up soon. I know y'all. Are y'all tired? Yeah. Rough week? All right, that's exciting. All right, so a 10-kilogram kid comes down a slide. So I'll draw the slide as a triangle. It is 3 meters high and 5 meters long. Okay. And there is a 10 Newton frictional force, or a frictional force, acting up the inclined plane that is 10 newtons that acts along the entire length of the slide. How much work does friction do on the kid as he comes down the slide? Oh, well, this is easy, actually. I thought this was hard. Not hard. What's the work that the frictional force does? Well, I know the magnitude of the force. I know the distance over which it acts. So what's the work? Well, work is equal to F times D times cosine of theta. Although the angle theta is 180, so that's just going to be negative FD. So it's going to be the work he does is 50 joules. Oh, because the displacement,
Because he's going down the slide?
yeah, he's going down the slide and the force is up the slide. Yeah, I wasn't really discerning between plus and minus on this. I was just looking for the work. It's not the magnitude of the work because it's not a vector, but just looking for the value of the work. But it should be minus 50. Or 50 is the right answer. Right? Number 5 is a lot like the roller coaster problem. This is like the cheerleader problem that we did. Did y'all go try that out, by the way? Throw your cheerleader friends up into the... No. Okay. So throws straight up with an initial speed equal to 10 meters per second. And I want to know how high does it reach? Look, at the top, only potential energy. At the bottom, only kinetic energy. So I say 1/2 mv squared equals mgh. Masses cancel. That's 1/2 of 100, or 10 squared, equals 10 times h, square root of 5. Wait, no, that's not right. No, h is equal to 5, excuse me. Okay.
The energy throughout the ball's entire path is the same.
Right.
It just matters where it resides. If it's
Right.
kinetic energy.
So yeah, I drew a figure in class where I said that the kinetic energy is right here, and the potential energy, I got none. But as it goes up, it shifts back and forth. So at the top, kinetic energy, I got none. But potential energy, it's all in potential energy. So it's going to trade back and forth, but the sum of those two energies will always be the same. That's the conservation of energy. Except when I have non-conservative forces like friction acting, and then those will act to take away energy. That's why things will come to stop with those forces at play. Oh, let's look at this one, number 6. The inclined planes in this case have friction. Which block is traveling the fastest at the bottom of the inclined plane? So all of them start at the same height, so they all have the same potential energy. And in fact, if there was no friction, which one would be going faster? Try again. If there was no friction, the kinetic energy at the bottom would equal the potential energy at the top. I know you think A, like A seems to be the most reasonable answer, but in fact, if there's no friction, they would all be going the same speed.
I was about to say if they're both equal.
Yeah, but if there's friction, which one's going to be going faster? What do you think? Huh? A, right. The reason for that is that this acts over a shorter distance. The frictional force acts over a shorter distance, so that friction doesn't take away as much energy. Okay? So the answer would be A for this question, but I've rewritten this question in the past, and I say, what if there is no friction? If there is no friction, they all go the same speed. Okay? But if there is friction, then A is going to be going faster, because that friction takes away less energy. All right, number 8 is similar to what we've done, except I have this spring-loaded gun. It's a little bit different. I have this spring-loaded gun, shoots a ball up into the air, and it goes up, comes back down. And I want to know, I tell you that it goes up to a height equal to 5 meters. H equals 5 meters. And I know that the compression down here, well, I'm looking for the compression. So at the top, it has potential energy, mgh. At the bottom, it only has elastic potential energy. So this is similar to the one that we wrote before, where we said 1/2 kx squared equals 1/2 mv squared, except all that energy is now going into gravitational potential energy. But the idea is the same. Right? I'm just setting these two energies equal. And now I'm looking for x. So I solved that for x. The mass is 0.02 times 10 times the height of 5. 0.2 times 5. 1 equals to 1/2 of k, which is 250. 250x squared. One divided by 125. Square root of that. I get 0.089 meters, which is 8.9 centimeters. Okay. I'm sorry, I was messy in that. Let me do it a little more clearly. So I'll do it over here. 0.02, that's the mass of the ball, times g, that's 10, times the height, which is 5, is equal to 1/2 of k. K is 250 times x squared. And I solved that for x. This is equal to 1 divided by 125. The square root of that gives me 0.089 meters. But to convert that into centimeters, it's going to be 8.9 centimeters. Sometimes with springs, we'll just talk about them in centimeters, because often with springs, you're compressing them small amounts, so we'll talk about them as centimeters. You would stop right here for this exam. All right. Particular questions? By the way, these were the free response. It'll probably be similar for y'all for your free response. A lot of these are the same. Yeah, I think we've worked most of these. Oh, the expression that represents power. Remember, power is energy over time, or maybe work over time. Either of those would be correct. Here, this is potential energy, this is work, this is kinetic energy, so C is the right answer. All right, do you have any particular questions? Well, I think that's a pretty good review of what we'll see on the